This is the part 2 of our lecture on photovoltaics, and in this section we are going to talk about the irradiance, and that is essentially a measure of solar radiation hitting the earth. So, we look at the definition of it and how it is used to evaluate how much we can collect solar energy on the earth and so on and so forth. So, the one of the issues we talk about when we are considering the PV system installation, or we can talk about PV commercialization. One is the system cost. We referred to that little bit in the previous section, where we talked about the levelized cost of energy, and it is we want to bring it down to about 15 cents a kilowatt hour. So, for that to happen, we have to consider what is called the system cost, and another important one is the insolation, and that is the irradiance part of it we are going to talk about. That is the average sunlight that is hitting the solar panels, and then for to consider grid parity, we need to think about local price of grid based electricity. Okay, we are going to talk about in this section about irradiance and how it is related to commercialization of the PV. The key factors for commercialization are given what is called the system cost and the insolation, and this is a very important factor. This is essentially the average sunlight that is hitting the solar panel on earth, and the other one is called the local price of the electricity, and this will allow us to see whether we need any subsidies or not, and also this is when the cost of levelized cost of electricity is equal to the conventional sources, then we call it a grid parity. The variables which are most important for this is insolation, or what the sunlight, that is essentially the amount of sunlight available at the location to be served. So, that is what we will be talking about in the next few slides. The definition of irradiance is given right on the top, which is given in terms of the watts per meter square, and this is essentially the rate at which the energy, the solar energy is incident on the surface per unit area of the surface. So, you can see the watts is the energy unit, and for the square the surface area given in terms of the meter square. And the irradiation, which is commonly used, is given by the joules per meter square, and this involves the time. Essentially, the irradiance is given watts per meter square. When you talk about over a period of time the irradiance, then we define what the irradiation, and sometimes this is also called the insolation, and this is the commonly used term in if you are in the business of photovoltaic installation, and this is the term people use called the insolation, and this is given by simply the integration of the irradiance, which is watts per meter square, over a specified time. So, insolation is given either per day or per year or per hour, and depending on how we do it. And then there is another term called radiosity, which is the rate at which the radiant energy leaves the surface per unit area, and this include of course the emission, reflection and transmission. So, if you look at the global irradiation or insolation, and this we talk about the latitudes in North America and Europe. Excuse me, I need to, okay. We talk about the latitudes covering from 30 degrees north to 60 degrees, and Stockholm is somewhere sitting right here, and this is given on the vertical axis is the insolation, that is kilowatt hours per meter square per year. So, essentially the A represents the entire year, and as you see, as the latitude we are going to the southern latitudes, and then you can see the insolation is going up, and I put a shaded area here, and when the insolation is greater than about 2000 kilowatt hours per meter square per annum, and that is conducive to use the concentrated solar power, which you have studied previously. So, when you reaches this, and this is typically reached in the southwest portion of the United States, that is in the states of Nevada and California and Arizona, and in fact that region is where most of the concentrated solar power plants are installed. But typically, as you can see, that when you come to the latitude, very low latitude like Stockholm, you see the insolation is about 1000 kilowatt hours per meter square. So if for example in India and things like that, they are somewhere around this latitude, and they have pretty good insolation. So they have typically between 1500 to 2000 all over the country. So there are other effects here, and the insolation, of course, when it comes from the sun to the earth, and there is the atmospheric effects on the solar radiation, and these effects are in terms of the scattering and absorption of the, for example, the clouds which have the water droplets which scatter the solar radiation, and of course there are also the absorption taking place, and when that happens we call it a diffused solar radiation. But when there is no atmosphere, then we have what's called a direct solar radiation. We talk about that a little bit more later on in this section. Some of the radiation, of course, received in the Earth's surface is redirected in the back to the space, and what I have shown here, the reflection coefficient, that is the fraction of energy reflected from the Earth back into the atmosphere. As you can see, this is where the Sweden is, for example, and there is a lot of reflection going on here, and you can see that's because of the Arctic with a lot of snow, as you expect it in the southern hemisphere and northern pole and southern pole. You see the reflection is quite high. So most of the solar energy is reflected from the ice. In fact, one of the reasons we worry about the ice disappearing from the Arctic in terms of the climate change point of view is because when the snow disappears, the reflection coefficient goes down, as you can see here, then most of the radiation is going to be absorbed by the water, and then the oceans are going to get warmed up, and then of course its entire cycle is going to be altered, global circulation. So one of the key factors we worry about in the climate change is the reflection coefficient both in the North Pole and the South Pole, and you can see that is quite high. That is because of the snow that is present there, and the rest of the locations, as you can see, reflection coefficient is quite low. And so this is an important fact. The reason I included this slide is to point out the importance of the snow cover or the ice cover on these north and south poles. So when you look at the insolation, and this is all the irradiance, this is the irradiance which we talked about, watts per meter square, and this is, for example, this is a typical location in Albuquerque, New Mexico, where you can measure the solar insolation, and this is from the morning to the evening. What you can see, this is the normal direct normal insolation. This is called the DNI, and the global insolation that includes both the DNI and the diffused solar radiation is given by the red curve, and the diffused radiation is given by the blue curve. And so you can see that when you don't have any clouds and the sky is very clear, what you measure is a much higher insolation. But most often, in fact, in desert areas in the southwest of Arizona and California, you don't have many clouds, no rain, most of you know. In that particular case, most of the insolation what you observe is the direct normal insolation. But in the rest of the country, where there is, for example, in Florida, although it is called the sunny state, but most of the time the humidity is very high in Florida, and you have water droplets in the atmosphere. As a result, you get a lot of diffuse radiation, and hence the typical insolation which you see during the day, it looks more like this curve as opposed to this curve. And so this is important, that tells you the effect of the atmosphere on the insolation. And if one can calculate this is a empirical formula which is given by these people all around the world. If you know the solar altitude, for example, which is given in degrees. This is the solar altitude. You have learned about that in the first part of the solar energy. And then if you know the geographic altitude, which we know, these two quantities are known, and this is the solar altitude and h is the geographic altitude. If you know that, you can calculate insolation by using typically this formula, and this will give you in terms of the watts per meter square, the integrated over time per day or per year, then you get the total insolation. And this is the global part, which has both the direct normal insolation and the diffused insolation. So, this is a simple way to calculate, but however, in most locations people have already measured this, and either through satellites or from the ground based measurements, and these are tabulated for any location around the globe. And if you look at the Sweden, these are the different latitudes. You can these are the different towns where the measurements have been made. And in the next slide, and these insolation data, average monthly insolation data is given. In fact, the different towns here, and the Stockholm is sitting right here. The important observation here is, and most of the insolation is in the months of April, May, June and July. And so, you can, in these months, the solar energy can be captured quite well. These are the pretty much the pleasant months in the Stockholm, and you can see the sun is out, and you can see the insolation is quite high. But if you look at the total insolation over the year, which is a little bit less than 1000 kilowatt hours per meter square. So, you can still use solar panels in Stockholm, and but mostly they are useful in the summer months. Now, if you look at what is the potential one could get in terms of the over the whole world, and the theoretical solar radiation which is striking the earth is roughly about just about 0.2 million terawatts. That is the amount of the radiation coming from the sun, and the global albedo, that means the reflection coefficient over the entire globe, average it, and that is about 0.3. So, essentially that is 30% of it is reflected back into the atmosphere. So, the practically what you can collect is about 600 terawatts on the entire globe. And if you assume that, let us say we have 10% efficient photovoltaic panels covered all over the earth, then we can collect pretty about 60 terawatts of power. And this is only on the surface, not on the oceans. And the estimated global demand is about 20 terawatts in 2050. So, you can see that there is a plenty of insolation hitting the earth, and we can, if you use the simple conversion efficiency of 10%, you can essentially run the entire electricity generation using the photovoltaic panels. Now, the question is the cost of the photovoltaic panels put all over the earth. And here there is an estimate here, these circles, these dots which are shown here, that is the area needed to supply the electricity for that particular region. In this particular case, this is North America and the Middle East and Asia and so on and so forth. And each of these dots represents about 18 terawatts and at 8% conversion. And this was done little bit less than that. And the solar irradiance is given in the color chart here, and you can see near the equator, for example, you have tremendous irradiance, and as you go to the north and the south poles excuse me, average sunlight goes down. So, most of the areas which in fact this is United States where I was talking about previously, this is the region California, Arizona and Nevada. This is where a lot of the insolation is. And in fact, in Africa and in South America, you can see the insolation is highest on the western part of the coast. And although Brazil, one would expect there will be a lot of insolation, they are very close to the equator. However, it is not as high as expected. That is because mostly of the humidity in the air, and atmospheric conditions are not conducive to have the highest insolation in that part of the area. But however, they have pretty good. This gives you about 250 watts per meter square on the average. So this is the average sunlight in this region, and India, for example, has about the same. So wherever you see this red color, that is ideally located to use the solar energy to generate power. So there is plenty of radiation hitting the ground, and this is typically if you put a flat plate tilted at latitude angle. That means whatever is latitude, for example, in Stockholm the latitude is about 59 degrees. So you point your panel to the south at the latitude angle, that is where you collect the maximum insolation averaged over the year, and you can, in this particular case I am showing United States, and you can see the maximum amount of insolation is observed in this part of the country. And this is essentially, most of you know the geography here. This is where the California is, and this is where most of the CSP plants are located in this region right here, and that is where highest insolation is shown. And you can see, as I mentioned before, Florida already, although it is sun is shining most of the year, but the insolation is low because of the humidity. There are a lot of rain, most of you know there, and the humidity is very high, so water droplets in the atmosphere, as a result you do not get much. So the average insolation varies from 2.19 kilowatt hours per meter square per day to about 6.78, and typically what you like to have for the solar installation to be effective is around 5 kilowatt hours per meter square per day, and then that becomes good enough to have a reasonable cost, and then the levelized cost of energy will be in line with the conventional energy. Now another aspect of this, when you are doing the CSP, this is, I think you must have seen it already, and this is you are tracking the sun. That means your solar panel is always sun goes east to west. So essentially your panel is tracking throughout the day where the sun is directly shining on the collector, and then you can see the insolation can be quite high. Here, for example, you can see some up to 9 kilowatt hours per meter square per day. So you can see that this black color here, you can get very high insolation, and this is where, for example, most of the CSP plants in the United States are located, these dark colors. So if you put a CSP plant here, you generate a lot of power. There are close to about 4 gigawatts of CSP plants have been installed now, and they are operational. And so when you have insolation that high, two-axis solar tracking works quite well. So this I think is will give you roughly an idea of insolation, how much solar radiation can be collected and where it can be collected, and how it is useful in calculating the levelized cost of energy. Okay, thank you.